All right. Hi again. In this video, we'll be going over logistic models, and that starts on page 32 in your packet. So this is pretty quick and straightforward. This is the general exponential model is y equals ab to the x. This is a form that you're familiar with, where a is, we know a as the initial value, right? So you can say a is the initial value. Some of us will call it the starting point, the intercept, right, etc. And so a is the initial value and b is the multiplier. Now remember, or recall, b is what? B is 1 plus or minus r, right? So it's 1 plus or minus the rate. Now the general logistic model is given by this. This is the formula for the general logistic model. You may see it differently in different books. Sometimes it's k over, it's more complicated, k over 1 plus k minus p naught, all this over p0 times e to the rt or negative rt. You don't need that. This is what you need from it, right? This is really what you need. Now it says, so let me explain what this is, right? Let me just explain what are these elements. Now, y is basically your f of x, or your dependent variable. A here is what we know as the capacity. So I'm going to give you an idea what that is. A is the capacity. Okay, and we don't want to delve too deep into that, but basically it's the maximum, right? It's basically the limit of y, right? The maximum y can be is a. Just think about it. This is 1 plus, right? So if you have a divided by 1 plus, for you to get a maximum value, right, this has to be the lowest possible, right? For you to get a maximum, this has to be the lowest possible. So basically, when the denominator approaches 0, right, that's when a gets maximum. Now, the denominator is 1 plus something, so that cannot approach 0. We have to think about this value here, right? So if you have b e to the negative kx be the minimum possible, right, that makes the denominator the minimum possible, and therefore that makes a over that the maximum possible. So basically when y approaches a, that means when this approaches, this is 1 plus, so you cannot have less than 1. It's 1 plus an item. So when this approaches 0, y approaches its maximum, its capacity, which is a, basically, okay? Now, b, what is b? B is also another parameter, right, that affects the starting points and all this and the growth of the curve. So, and k is what we know as the growth rate. So you don't need, again, to learn or to know more in depth about this. It's just a model. It's just a function that you're going to be using. At this point, I'm okay with you just knowing. Let me just erase this. At this point, I'm okay with you just knowing the equation itself and just applying it correctly. So it says, based on the graph, why do you think the logistic model are a better approximation for the population growth than exponential models? So why do we think that, right? What makes them better? Now, if you were to graph this logistics model, it's normally going to look something like this. It's going to, right, and it's going to plateau up. Now, when we graph exponential, this is the logistic, right? This is the logistic model. When you graph exponential, it's going to go more like this, right? So you know that exponential, the ab to the x, right? You know that's not really realistic. That's not really what's happening in real life, right? So that's why the logistics model, it shows basically, first of all, you have a maximum, you have a capacity, you have like a stopping point or the maximum possible value, unlike ab to the x, where if this goes on exponentially, right, then it doesn't have a maximum, which in real life is not possible. It's not realistic. So that's one of the reasons, right? And also models in real life in actuality are finite, so they'd have to stop somewhere. So that's one. And also, this S-shaped allows you to show like an initial slow growth here, and then a rapid growth, and then you kind of plateau a little bit, right? You kind of slow down a little bit. So this is more actual, right? More realistic than having something starts like at 0 or 1 and just keeps on going indefinitely, which is not going to be applicable in real life. Okay, so that's one of the reasons, right? That's one of the reasons. This is a more realistic, the logistic model is a more realistic. Now it says, so with this model being what it is, right? So again, it's more like an S-shaped versus your traditional AB to the X. To find the initial amount, where would you find this on the graph, right? So the initial amount, when they say initial amount, that means what? That means when X is equal to 0. And if X equal to 0, what happens? You'll have A over 1 plus B multiplied by what? By e to the 0, right? This is going to be 0 here, which makes it e to the 0 is 1. So basically, you'll have A over 1 plus B, right? That's your initial amount. That's how you find it. So your initial amount is going to be that value. And then it says equations of horizontal and vertical asymptotes. So those are going to be aware. Think about what happens as X increases, etc., etc. So if you want to find the horizontal asymptotes, they're going to be at y equals to 0, right? Y equals to 0, which is the x-axis, so it's going to look something like this. You're going to start probably something like here, right? You're not going to go below that value. You're not going to go in the negatives. You have an actual value. And you're not going to go beyond, we just said the capacity, right, A? You're not going to go beyond A, whatever that value is. If A is here, you're not going to go beyond this value or here, in this case, whatever it is. Okay, so those are the equations of your horizontal asymptotes. Now, what is the limit? I just mentioned that. The limit to growth, that's your capacity, right? The maximum possible, and that's A. And where does the function grow fastest? So again, we talked about this looking more like an S model, right? It's looking more like this, really. So it's growing fastest at what we know as the point of inflection, okay? So that's where the function grows the most. Okay, now you can see that here, maybe think of it as in terms of slope, right? This is like the steepest possible slope, all right, at the point of inflection, where that change occurs, all right? So those are just, those are basically pointers about this logistic model. Let's see what else on this page. Let's try an example, okay? So, and think of this point here is the point where the curve transitions from accelerating growth, so here, this point, right? From an accelerating growth to a decelerating growth. So this is going fast, 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 and then it's slowing down. Okay. And normally, just I'm going to add more in a piece of information, this normally happens at halfway through the capacity, okay? It's like at A over 2, like this point here. This will be like A, right? This would be 0. All right, so with this said, let's apply this knowledge. Example 1, on a college campus of 7,500 students, one student returns from vacation with a contagious virus. The spread of the virus is modeled by y equals. So they're giving you a logistic model, right, that shows this spread of the virus. Then it says, so the equation is given for t greater or equal to 0, where y is the total number of students infected, right? That's what y represents, the students that are being infected, that's y. The college will cancel classes when 30% or more of the students are infected. So, okay. If 30% or more of the students are infected, the class will be canceled. How many students will be infected after 4 days? So all I have to do is apply this for t equal to 4. So you're finding basically f of 4 or y of 4, right? you're doing y of 4, f of 4. So you're going to have 700, you're doing f of 4. 7,500 over 1 plus 74.99 times e to the negative 0.9 times 4. This is times here, right? Remember, t is in days. Remember, when it says after t days, so when the equation is presented to you and it says after t days or t minutes, that means automatically use t days, right? Use days as the main unit. If it says the formula for t minutes, then use minutes as the main unit. Okay, it's the formula that dictates, right, what the value of t should be in. So by doing the math on this, how do we solve for that? You're gonna have, you just plug this information in the calculator. You're gonna have about 36.42 something. So let's say about 36 students. Okay, students. So that's the number that you're looking for. And then for part B, it says, after how many days will the college cancel classes? So how do we do that? How do we do after how many days will the college cancel classes? So think about it for a minute, maybe pause the video and think about what's going on here. Right? Remember, the college will cancel classes when 30% or more, right, are infected. So how do you do that? You have a total of 7,500 students. So if you have 30% of that, you're going to do 0.3 times 7,500, which is going to be 2,250. Right? This is the number you're looking for. So you're going to say 2,250 equals 7,500 divided by 1 plus 74.99 to the, or times e to the negative 0.9 t. Okay? So remember, it says after 30% of the students or more are infected. So 30% of the total, 30% of 7,500 is 2,250. So you want that number to be equal to the formula, and you set it up and you solve. So maybe take a moment and see if you can solve. Pause the video, see if you can solve this setup, on your own, and I'll give you the answer. So pause, give it a shot, and then play again. The answer is going to be t about 9 days. Okay, so basically that is the end of this question. Give number 2 a try on your own as a practice problem, knowing the logistic function now, and then we will complete this either as a warm-up next time or by the end of the class. Thank you.